Assalamualaikum warahmatullahi taala wabarakatuh and good morning. I'm Dr. Sababau from the Physics Section Pusat Pengajian Pendidikan Jarak Jauh, University Science Malaysia. This is course JRF 318 Quantum Mechanics. We are in chapter 4 Solutions of One-Dimensional Time-Independent Schrödinger Equation. This is unit 4.5. We are still in unbound states. Now we will discuss tunneling. That means the ability of a particle to go through a barrier, a potential barrier. The objective of this lesson basically is for you to be able to describe and determine how a particle may penetrate a potential barrier. The question, what happens when the step has finite width? Okay. Previously we had discussed the transmission and the reflection probability of a particle by a step potential well or wall. Okay. Yes, when E is greater than the potential V0, the particle can be anywhere, but after crossing the wall, the intensity or the transmission probability decreases. Okay, due to the difference in between the potential and the energy of the particle. If the energy of the particle E is lower than the potential V0, of course the particle will be reflected back, but the wave function inside the wall or the potential with V0 is not zero. There is a probability for the particle to penetrate the wall. Okay, now what happens if the step potential has finite width? That means zero potential, then go up to V potential, V0 potential, and go down to V0 again. Let a step potential has V0 for x less than 0 and x greater or equal than A, and in between, that means between 0 and A, let the potential be V0. So the diagram look like this. Okay, at x equal to 0, to the left, it is V0, V0, that means no potential. And also to the right of A, we have V0. In between, we have B equal to a Stern value of potential V0. Okay, and now let us consider when E is smaller than V0. That means the energy of the potential, or the energy of the particle is lower than the step potential here. Okay, sometimes if this is the look of the diagram, it is also called barrier. That means sawar atau pengadang. It's look like a wall where you have the potential is equal to 0 on both sides of the wall. Okay, as in the previous case, we mark the constant or the coefficient A1 and B1 for the region to the left of x equal to 0. Inside the potential barrier, let us mark it as A2 and B2, and on the right of x equals to A, that means values greater than x equal to A, we mark it as A3 and B3. This is the potential used in the equation. Okay, and the direction of the arrows indicates the direction of motion of the wave function. Okay, in the previous case, we remember, I hope you remember that when the source or the particle is from the left, that means there is no probability of any particle coming from the right because there is no source of particle from the right. So later we'll see that B3 will be set to 0. Okay, this is how we look at the diagram. Assume a particle is incident from the left. Okay, from the left, that means from negative infinity with energy E, energy of the particle less than V0. In classical physics, the particle will always bounce off and reflected back to the left. In classical physics, if you have a particle from the left here, going to the right, it will hit the wall, then the particle will be reflected back. That means 100% if we think of in terms of classical mechanics or classical physics, the any particle coming from the left and hitting the potential barrier wall will be reflected back. Quantum mechanics, the particle will sometimes be able to tunnel completely through the barrier and emerge on the other side. Of course, in quantum mechanics, we'll also get a value for the probability of reflection. That means, of course, some particle will be reflected back, but there is a probability of some particle to penetrate or pass through the barrier. This is what we call as tunneling. Some particle will tunnel through the potential barrier. Okay, let us recall. The particle penetrates into classically forbidden zone when we were talking about step potential when E is less than V0. Okay, some particle will penetrate into the classically forbidden zone. The classically forbidden zone is the region where V equal to V0. If the potential is reduced to 0 after a finite distance, that means if the V equal to V0 is up to only a certain distance. Finite means that there is a certain distance, then the wave function spill out on the other side where it oscillates. Okay, so if the width of the barrier, this is the width of the barrier. In the previous case, we had discussed step potential. That means the V0 will stretch to infinity. But now, no more. Finite means that a certain distance, let the distance be A, we will find that V equals to 0 again. Okay. This potential yields three distinct solutions to the Schrödinger equation because we have three regions now. That means region when x equal to 0 and less, region between 0 and A, and region A and to infinity. So there are three regions. So we put the wave function psi1 as before. Okay. Of course, we have replaced the term energy with K here, K1. Okay. And again, you remember that since now V0 is greater than E, so V0 comes first. Okay. So we have these two equations for x less than 0 from 0 to A, and the third one when x is greater than A. The solution for x greater of A is similar to the solution for x smaller than A, with the leftward moving part of the wave function deleted. Why? As I said just now, B3 comes from positive infinity. Since the source of the particle is from the left, that means from negative infinity, so there shouldn't be any particle from the right hitting the wall. Where is the diagram? Okay, this B3 actually representing the movement of particles from positive infinity hitting the wall. So since the source is from the left, the source of the particle, so there is no, we don't expect any particle coming from positive infinity hitting the wall. So B3 is set to 0. That's why the third equation, we have only A3 there, no B3. Okay. Now we have two pairs of boundary condition because we have two boundaries at x equal to 0. This is the first boundary condition. That means the wave function should be continuous. That means psi1 equal to psi2 at x equal to 0. Then we have this relationship A1 plus B1 equal to A2 plus B2. And also the differential should also be equal, so that the gradient is continuous at the boundary. Okay, so we have this ik1 a1 minus ik1 b1 equal to k2 a2 minus k2 b2. Okay, now at x equal to a, that means the second boundary, we have this relationship psi 2 must be equal to psi 3, and this is another equation number 3. And also the differential of the wave function at x equal to a is given by this is equation 4. Okay, now we have 3 unknown, but we have we have 5 unknowns actually. We have a1 b1 v1 I repeat, a1 a2 better look at the diagram. a1 b1 a2 b2 a3, and b3 is not there because we set it already to 0. So we have 4 equation, but we have 5 unknowns: a1 b1, yeah, a2 b2, then a3. Again, as in the previous case, we try to set we are looking, let's say for this transmission probability, we are looking whether any particle will reach region 3. That's why the transmission probability here is basically in region 3 with respect to whatever probability in region 1. That means the probability of transmission of the particle with respect to the incident probability of incident particles. That means region 3 with respect to region 1. Okay, so transmission probability is given by A3 conjugate multiplied by A3 divided by A1 conjugate multiplied by A1. So it is quite tedious mathematics. Then we have this solution, and you see that it is in terms of sin, yeah, not sine, but sin trigonometric function. Okay, so we have this relationship. What it means here, whatever the value of sin is a trigonometric system. That means the maximum is 1, the minimum is maybe negative 1. T is non-zero. Okay, T is non-zero. Even if sin is 0, you can see here 1 over 1. That means equal to 1. If sin is equal to 1, then 1 over 2. Okay. Then if sin equal to negative 1, you have to multiply with this. That means there will be always be a value for T, the transmission probability. It is not 0. So T is non-zero when E is smaller than V naught. What it means when transmission probability is not 0, that means a particle can tunnel through the barrier and emerge on the other side of the barrier. Okay. If according to classical mechanics, all particles coming from the left hitting the barrier will be reflected back. But in quantum mechanics, of course, there are some particles which will be reflected back, but some particle might be able to tunnel through or penetrate the barrier. This is a schematic diagram showing it. The particles tunnel through the classically forbidden region. Classically forbidden, that means in classical mechanics, whatever is to the right of the first wall here is forbidden. The amplitude is reduced, but the wavelength remains unchanged. Since we are using wave mechanics in quantum mechanics, so basically it looks like this. The wave function is not completely to 0 when it penetrates the wall. If the wall thickness is small enough, that means thin enough, then the wave function might penetrate on the other side, except now the amplitude is reduced, but in terms of the wavelength, that means the frequency is maintained. So this is what we can see here. Some of the wave will be reflected back from the direction of incident. Then some of it might be penetrate the potential barrier wall. So this is how in quantum mechanics we can see that some particle will penetrate the potential barrier, and the prediction by quantum mechanics agrees well with experimental data. That's why we have to accept it. This is the proof by using Schrödinger equation that some particle can penetrate a potential barrier. Okay, let us look an example. For example, people will always say, if a particle can penetrate a potential barrier, can a baseball tunnel through a wall? Can a ball, such as baseball or tennis ball, tunnel through a wall? Because in classical mechanics, usually we talk about ball, marble, okay, colliding with a wall and so on and so forth. So if we claim that a particle can pass through a potential barrier, can a baseball tunnel through a wall? So let the mass of the baseball be 0.14 kilogram. Let's say this is real, just typical values, okay, and assume that it is tossed gently at 1 meter per second. That means it's non-relativistic condition, okay. That means you can use normal mathematics. We have this relationship P equal to H bar multiplied by K. So we can determine what is K2, okay. P per H bar, we have this value. Let the thickness of the wall here, is missing there, of the wall be 0.2 meter, okay. Let's say the thickness be 0.2 meter, that means 20 centimeter, okay, 20 centimeter. We have to determine what is K2A is equal to 2 to the 0.6 multiplied by 10 to the 32. Why we need to determine K2A? Because it is inside this transmission probability equation, and later we have to determine Shin squared K2A. So K2A is this and this. Then Shin will be, we use the Taylor series for Shin, okay. There is a series. It is about exponential to K to A, and we put in the value of K to A, and finally we get 10 to the power of 10 to the power of 32. How big is it? You can imagine. Okay, it is very, very large value. Okay, it is about 10 to the power of 10 to the power of 32. It's about that. This is such an enormous number, then that the factor multiplying Shin square K to A is of no consequence. If you look back at this equation, if this is already 10 to the power of 10 to the power of 32, then basically whatever the value here is negligible. I mean, does not play any role at all, because this number is very, very big. So basically even 1 is not relevant. You have 1 plus 10 to the power of 10 to the power of 35. So basically very, very big denominator here. So 1 over a very, very big number, what you get is a very, very small transmission probability. Okay. So the transmission probability is 10 to the power of negative 10 to the power of 32. Almost unimaginable tiny probability. We cannot imagine, very, very small. Even our calculator or even our PC might not be able to calculate this. Okay, so we do not observe baseball tunneling through walls. That's why in everyday life, yes, theoretically according to quantum mechanics, that ball should be able or have non-zero probability of penetrating the wall. But since the value is very, very tiny, very small, so we in everyday life do not observe a baseball penetrating a physical wall. But still, there is a non-zero. You cannot say that t equal to 10 to the power of negative 10 to the power of 32 is 0. No, it is still not 0. But very, very, very small number. So in other words, the probability determined by using quantum mechanics is correct. And even if it is applied to a baseball in real physical world, it is also correct because the value given here is correct. That means the probability for a baseball passing through a wall is very, 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 a few very lah, small. Okay, that's why we do not see a baseball in everyday life passing through a physical wall. Okay, in conclusion, a particle may penetrate a finite width potential barrier. Thank you very much for your attention.